Gonna be just doing a bit of review at this first part for part A, but let's read what the situation is. So, uh, they have that the height of water in a storage tank during a 15-hour period is given by a twice differentiable function h of t. It's measured in feet, and t is measured in hours. It goes from 0 to 15 t, so 0 to 15 hours. The graph of h is concave up, and that's actually a key thing. We're going to need to take note of that. So h is concave up, let's remember that. Then the next thing that we have on this entire interval, so it's concave up on this entire interval. Then we have that certain values of the derivative of h are given in this table. They also give this added piece of information, which is actually relevant for this problem. And at first I was curious, I was like, how am I going to do this? They don't give me h, but then I read it again, and I saw that they gave me this piece of information, which is crucial to doing this first part. So it says, use the tangent line approximation for h at time t equals 2 to estimate the value of h of 2.8, the height of the water at time t 2.8. Is the approximation an overestimate or an underestimate of h of 2.8? Give a reason for your answer. So the key thing here is that we need to know that the entire time from 0 to 15, the function is concave up. So being that the value of it is that h is concave up, so that's concave up, whatever. I have no idea. So this is h of t. So what they want to do is use the tangent line approximation at time t equals 2. So here's 2. The tangent line approximation for h is this function right here. So t equals 2, that has some straight line tangent to it, right? And it looks like this. And since h of t is concave up, the tangent line is going to lie below the curve, and that's what's key in answering this part of the question. But why? Why is that? So this tangent line approximation, what you do is 2.8 is somewhere over here. We don't know what h of t is. That's this value right here, h of 2.8. We don't know what that is. That's this exact value. But I can get what the value is for the tangent line approximation is. So let's distinguish between these two things. So that's this value. This is the tangent line. The pink dot, right, that's the tangent line approximation. And the blue dot right here, that is h of 2.8. And ideally, this difference between these two is not too much. Okay? And that should be an approximation. This pink dot should be an approximation for this dot on the curve. But first I need to find out what this line is. So let's get what's called the linear approximation of this h of x. So h of x has a linear approximation. So let's write L of x equals linear approximation or tangent line approximation. Linear approximation. It's the same thing as saying tangent line approximation. Linear approximation, tangent line approximation. For h at t equals 2. And this is hopefully going to be that's the whole thing. It should approximate values of h of x near t equals 2. I should say t, sorry. Let's change our variable to t. And yeah, so how am I going to do this? Well, I know the slope of this line. How do I know the slope of this line? Do I know h prime of 2? Yeah, that gives me the slope of the tangent line. The slope of the tangent line they give me right here. H prime of 2 is 0.3. So I know the slope of this line. Now, what I was curious about was, do I know a point on this line? And I was like, at first I was like, no, I don't know what point this is right here. I don't know what h of 2 is. But then I read, at time t equals 2, the height of the water is 7 feet. And h, okay, is h of t models the height of the water at any time t, h of t. So they're telling me h of 2 is 7. So now I have a point. I have 2 comma 7 as a point. And I have a point and I have a slope, so I could get the linear approximation. I could get L of t. L of t is just the equation of this line. L of t equals L of t, or I could write it in terms of y, right? Point slope form. So let's just get y, or right, y minus y1 is equal to m times x minus x1, right? But the variables, what's y? Y is what I'm looking for. I'm looking for L of t, right? y1 is 7. I'll add it over to the side, y1, right? M is 0.3. Instead of using the variable x, I'm going to use t minus, the t value is 2, and then y, don't forget, was 7, plus 7. That one's going off, so L of t, make sure we know, right? I'm just using point slope form. I have a point and I have slope. My point is 2 comma 7. I found that out because when the time is 2, the height of the water is 7 feet. So this point is along 7 here, and it's 2 along t. So I have a point and I have slope. And then I'm just writing the equation of that line as L of t, a linear approximation or tangent line approximation. So I'm just writing the equation of the line. I'm writing it y equals, right? I could write it y equals y minus y1, and then I solved for y is m times x minus x1 plus y1 when I solve for y. So that's just L of t. Y is L of t. Okay, it's a linear approximation. And what did I get? I got 0.3 is the slope. I don't like x along the x-axis. I want to use t as my variable. T minus the t value, the point is 2 along t, along x, plus my y value is 7. And they want to use this linear approximation. Again, this value, L of 2.8, what the line gives you should be close to what the curve gives you. So now I do L of 2.8, and I can find out what this is. This is 2.8 minus 2, which is just 0.8 plus 7. So 3/10 times 8/10. 3/10 times 8/10 is going to be 3/10 times 8/10 is 4/5. This is 2, 5, 25, 6/25 plus 7. So whatever that is, 6/25 plus 7, that's 24. So it's going to be approximately 7.24. So this value right here is 7.24 on the line, which should be close to whatever h of 2.8 is. That's the idea. H of 2.8 should approximately be 7.24. And I just did 6/25. That's 24 hundredths, right? So 24 hundredths plus 7 is 7.24. And that's the idea behind linear approximation or tangent line approximation. Now the next one. So B, you want to find the right Riemann sum with 5 subintervals. So we have here, let's get a sketch of what this looks like. So here I have this one line, let's do another line, and let's just get a rough sketch of what this is going to look like. So from 2 to 14, and I also know that h is concave up during this entire thing. So concave up, that's concave up. I could do it any which way, but now I just need to be careful because I should have taken note of how these values are increasing. So for example, at 0.2, it's less than, so this should be 0.3. So let me sketch this again. Let's start off with doing, let's see, it goes up to 7.7, so I'll start low. And then the next value at 4, so 4, and then 5 is closer, then 8 is over here, then 10, then 14, it's not evenly spaced, who cares, 2.3, then at 4 it's 0.6, so this is another value, then at 5 it's 0.7, so right above that one, at 5 it's 0.7, then at 8 it's 1.4, so it doubles the whole thing, and it's going to go up to some crazy amount at the end, 8. And then 10 is 2.3, so let's say 2.3, and that's 2.3, let's say up here, and then at 14 it's at 7, let's say that that's way up here somewhere, let's just keep it in our minds, and they want us to use right Riemann sum with 5 subintervals. So the 5 subintervals are going to be these sort of 5 values. What does that mean? It looks like this. Here's the 5 rectangles that you're going to have. Here's a rectangle. The first rectangle you take is going to be this one right here. And that's with that 4 value at the end point, the 0.6 right here. Then the next rectangle is going to be this one right here. And the next rectangle is going to be this one. This is 3 rectangles. And the next rectangle you take is going to be this one. And this sketch just helps you out. It just guides you to approximate this value. And then the last one is going to be this big one way up here in the clouds. And now you just want to sit here and you want to find out the area of each one of these rectangles. Just be careful, right? The rectangles are not of equal width. So this first rectangle, so let's say R1, R2, R3, R4, and R5. So R1, you want to find R1 plus R2 plus R3, the 5 rectangles, R4 plus R5. Okay, so R1, the width is 2 for R1, right? It goes from 2 to 4, and the height is 0.6 plus R2, the width is 1 times the height is 0.7 plus R3, the width is 3 here times the height is 1.4 plus R4, the width is 2 and the height is 2.3. Then the last one, R5, the width is 4 times the height is very high, 7.7. And there's some key fact here. There's another thing that I want to do, which is I want to draw a rough sketch of what h of x is going to look like. And what do we have to remember? That it's concave up the whole time. So concave up looks like this, right? If I did this, it should be looking like a concave up curve, because that's going to help us for the next question. So you would find what this sum is, and then that would be the answer to this one. The next one, it says, is the approximation an overestimate or an underestimate? Let's see. So these areas here, right, for these rectangles, that's actually going to be counted in our sum, right? All of the area of the entire rectangle, which is going to be an excess of area. So our approximation is an overestimate. Whatever this value is an overestimate of the area underneath the curve. Okay, so overestimate. And the reason I know that is because the curve is concave up. If it were concave down and I did, it's concave down and I did right endpoints. So if I did right endpoints with it being concave down, then it would flip its role, right? Because the first value would be what? What would be the first value here? So right endpoints with it being concave down, what would it look like? Now, why am I drawing a blank? Because it should flip. For concave up, the right endpoints should be an overestimate, and they are. Now, why is it that right endpoints? So right endpoints here. Because what's this function doing? So as it is that, so if it's concave up and your function is increasing, right endpoints will be an overestimate. So let's look at the difference. Let's look. So here's concave up. Right endpoints at this point, right? So if it's right endpoints here, then it's going to be an underestimate. But since the function is increasing, the right endpoints will be an overestimate. And you can tell that the function is increasing along these things here. And then if you look at this concave down, the whole thing reverses. But you should just draw the picture and see what happens for concave up during its intervals of increasing. So this is concave up. And then this is concave down. And then that'll make it, you should see how it is if it's concave up, that this is going to be an overestimation. And you could say overestimate since h prime of t is up. Let's make sure, does it say h? It says h is concave up. Okay, good, yeah. So h is concave up. And then that means that my derivative is increasing, right? If h is concave up, if h prime of t is increasing, then h double prime of t is greater than 0. And then you know if h double prime of t is greater than 0, then h of t is concave up. And that's all. That's what's key here, because even if it looks like this, right? So this is h prime of t. I don't know what h of t is concave up. H prime of t, saying that h prime of t was concave up, isn't necessarily the case, because you could have it, look, even if it's increasing and it's concave down, it'll be an overestimation for right endpoints as long as it's increasing. So you're good. But again, this here, it's not necessarily true. This sketch here that I did of h prime of t being concave up, you don't know that, but you do know that h prime of t is increasing, and that's all that matters. If h prime of t is increasing, then this will be an overestimation. Look here. So here's h prime of t increasing with it being concave down, and then here's h prime of t increasing with it concave up. Look at what I have here. The right endpoints give me an excess of area. Right here. The right endpoints. And then here, I have it where if I do right endpoints, it will give me an overestimation. If h prime of t were decreasing, then the right endpoints would be an underestimation. Okay, and you could go through that one as well. Okay, now the last one. So the last one, we want to make sure that we see what's happening in this case. You write down the relationship between the limit of the Riemann sum, so limit, the infinite limit of the Riemann sum. This is the general case, right? F of x sub I delta, or k, let's use k as our indexing, k, delta x, k goes from 1 to infinity, is equal to the definite integral from a to b of f of x dx. And you want to relate everything that we have to this problem here. So I have it where it's going to be, let's see, limit, or in this case, yeah, they say the limit of this sum as n goes to infinity. So I'm going to do limit as n goes to infinity of this sum here. So k goes from 1 to n, and h prime, f, whatever, it doesn't matter, let's write h prime, that's fine. 15 over n, k minus 1, 15 over n. And now I want to see how this is going to equal f of x, and so forth. So it should be fairly clear that this inside value, and we should actually be taking, instead of x, it's actually t, the variable. We'll do it at the end. They say t because h in this original problem, it's h of t, and everything along the x-axis is t, but we'll do that at the end. So let's see what we have here. They say that it's a left Riemann sum, and that helps us out a lot, because that means that the first value that actually is going to be evaluated in this here, the first value is going to be your a value. So the first value is when k is 1. So when k is 1, 1 minus 1 is 0. 0 times the whole thing. And the first value that you're starting at when you do this, right? It's, again, make sure you know that it's an interpretation of from a to b, right? And if I'm doing left sums, the first value that I evaluate for the height of my rectangle is just going to be whatever a is. So I can get a by just plugging in 1 here and seeing what this inner value is. And I see that 1 minus 1 is 0, 0, so it's h prime of 0, so a is 0. And that's gonna start to help me out. So that's 0, this is b, f of x dx. Now the next question I want to ask is, well, what is f of x? It's just h prime of x, or h prime of t in our case, but whatever, h prime of x dx. Right, that's the inner value, and dx, right, delta x, is this 15 over n. Right? That's how we would match everything up. And now I have delta x is equal to 15 over n. And now I know that that's equal to b minus a over n is equal to b minus 0, n cancels out, 15 is b, and then I get 0 to 15 of h prime of x dx. But just go till along t, 0, know that the variable along the x-axis is t, in our case h prime of t dt is the interpretation of this at the end of the day. Just match everything up, use that definition that we have,